For more than a century, South Florida has been fighting a war against water. Every year, enormous volumes of fresh water that once slowly flowed through the Everglades are instead diverted into canals and discharged into the Atlantic Ocean and the Gulf of Mexico. At the very same time, millions of residents across South Florida depend on increasingly stressed freshwater supplies, while one of the world's most unique ecosystems continues to shrink. To reverse more than 100 years of environmental damage, engineers are now constructing one of the largest ecosystem restoration projects in American history. At the center of that effort stands a gigantic reservoir capable of storing nearly 78 billion gallons of water. Covering more than 10,000 acres, the Everglades Agricultural Area reservoir represents a multi-billion-dollar attempt to rebuild the natural water cycle of an ecosystem that was once considered impossible to restore. But why does America need such an enormous artificial lake? How are engineers building a massive reservoir on former farmland? And could this project finally save the Everglades after generations of human intervention? Join History Fade as we explore how America is rebuilding the Everglades with a $4 billion mega reservoir.
Long before canals, highways, and cities transformed South Florida, water moved very differently across the region. Historically, rainfall falling over central Florida gradually flowed south from Lake Okeechobee in a vast, slow-moving sheet of water. Early explorers described the Everglades not as a swamp, but as a river unlike any other on Earth. Known as the River of Grass, this enormous wetland once stretched across nearly 3 million acres, supporting countless species including alligators, wading birds, panthers, fish, and rare plants found almost nowhere else on the planet. But during the 20th century, people sought to control this water. Large portions of the Everglades were drained to create farmland and support rapidly expanding cities. Hundreds of kilometers of canals, levees, and pumping stations were constructed to move water away from wetlands and toward coastal communities. The transformation fueled economic growth. Agriculture flourished south of Lake Okeechobee, particularly sugarcane farming, while cities such as Miami, Fort Lauderdale, and West Palm Beach expanded dramatically. However, controlling water created unintended consequences. Instead of slowly flowing south through wetlands, enormous volumes of fresh water began moving east and west through artificial canals before eventually being discharged into the ocean. During heavy rainfall years, managers often had no choice but to release excess water from Lake Okeechobee into coastal estuaries to prevent flooding. These emergency discharges frequently carried large amounts of nutrients, especially phosphorus, into sensitive ecosystems. The result was devastating. Algae blooms became increasingly common, seagrass beds declined, fish populations suffered. Estuaries that evolved under delicate salinity conditions experienced major ecological stress. At the same time, areas farther south often experienced water shortages because the historic flow through the Everglades had been interrupted. Reduced freshwater flow also allowed saltwater from the Atlantic Ocean to gradually move inland, threatening underground aquifers that supply drinking water to millions of people. By the late 20th century, it had become clear that simply moving water faster was no longer a solution. Engineers and environmental scientists concluded that South Florida needed a completely different strategy. Instead of rapidly draining water away, they needed a system capable of capturing, storing, cleaning, and slowly releasing water back into the environment. And that vision eventually became the Everglades Agricultural Area Reservoir.
Constructing one of America's largest environmental reservoirs did not begin in a remote wilderness. It began on former agricultural land. The reservoir site lies within the Everglades Agricultural Area, a region south of Lake Okeechobee that has been intensively farmed for decades. Transforming farmland into a massive reservoir required engineers to completely reshape the landscape. First, extensive site preparation operations removed existing infrastructure, drainage systems, roads, and agricultural facilities. Heavy machinery then began moving millions of cubic meters of soil to create the enormous basin needed to store water. Unlike traditional reservoirs built behind mountain dams, South Florida presents unique engineering challenges. The terrain is extremely flat. In many areas, elevations vary by only a few meters across vast distances. Beneath the surface lies porous limestone bedrock that behaves almost like a sponge, allowing water to move underground far more easily than in many other regions. Engineers, therefore, could not simply excavate a giant hole and fill it with water. Instead, they had to construct massive perimeter embankments surrounding the future reservoir. These earthen embankments rise dozens of feet above surrounding land and stretch for many kilometers around the site. Building them required enormous quantities of engineered fill material, carefully compacted layer by layer to ensure long-term stability. Sophisticated geotechnical investigations continuously monitor settlement, compaction, and soil performance throughout construction. Once complete, the reservoir will cover approximately 10,500 acres and hold around 240,000 acre-feet of water, enough to supply billions of gallons for ecosystem restoration. But storing such an enormous volume of water created an even greater challenge. How do engineers prevent billions of gallons from simply escaping underground? The answer lies beneath the surface.
Although visitors may eventually see a vast body of water, one of the project's most important engineering structures will remain almost entirely invisible. Florida's limestone geology creates a serious problem for reservoirs. Unlike solid bedrock found in many parts of the world, South Florida's subsurface contains highly permeable limestone filled with cracks, voids, and interconnected pathways. Without additional protection, water stored inside the reservoir could seep away underground. To solve this problem, engineers are constructing an enormous seepage barrier system around the reservoir. This underground wall extends for many kilometers and reaches deep below the surface, forming an invisible hydraulic boundary designed to dramatically reduce water losses. Constructing the barrier is an extraordinarily complex process. Specialized trenching equipment excavates narrow, deep sections through soil and into underlying geological formations. As excavation progresses, bentonite slurry, a dense clay mixture, is pumped into the trench to prevent collapse. Once excavation reaches the required depth, engineered materials are installed to create a continuous low permeability barrier. The finished wall effectively acts as an underground dam. Even though it cannot completely eliminate seepage, it significantly reduces water movement, allowing the reservoir to function as intended. Engineers also employ extensive monitoring systems throughout the site. Groundwater sensors, pressure instruments, and observation wells continuously measure subsurface conditions, allowing operators to track performance over time. Without this hidden infrastructure, the entire project could never achieve its restoration goals. If you're enjoying these stories about the world's most ambitious engineering projects, subscribe to MegaBuild HQ and join us as we uncover the mega projects reshaping our planet.
Simply storing water is not enough. The water flowing south from Lake Okeechobee often contains nutrient concentrations far above what the Everglades ecosystem can tolerate. Phosphorus is particularly problematic. Even small increases can dramatically alter native plant communities and damage delicate wetland ecosystems. Rather than relying entirely on conventional treatment plants, engineers developed a remarkable alternative: nature itself. Before entering the Everglades, water stored in the reservoir will pass through enormous stormwater treatment areas, commonly known as STAs. These constructed wetlands function as giant natural filtration systems. Covering thousands of additional acres, they rank among the largest water treatment wetlands ever created. As water slowly moves through these wetlands, aquatic vegetation such as cattails and submerged plants absorb nutrients. Microorganisms living within soils and plant communities further remove pollutants through natural biological processes. Sediments also settle out as flow velocities decrease. By the time water leaves the treatment areas, phosphorus concentrations are dramatically reduced. This combination of engineering and ecology represents one of the project's most innovative features. Instead of fighting nature, engineers are using natural systems as part of the solution.
Once completed, the reservoir will fundamentally change how water moves across South Florida. During wet seasons, excess water from Lake Okeechobee will be pumped into the reservoir instead of being immediately discharged to coastal estuaries. The stored water will then move through treatment wetlands where nutrient levels are reduced. During dry periods, operators can gradually release treated freshwater southward into the Everglades. This restored flow is expected to provide numerous benefits. Wetland habitats may recover. Wildlife populations could improve. Coastal estuaries may experience fewer damaging freshwater discharges. Underground aquifers could receive additional recharge, and freshwater flow pushing toward the coast may help slow saltwater intrusion threatening urban water supplies. In effect, engineers are attempting to recreate, at least partially, the natural hydrological rhythms that existed before widespread development transformed South Florida. Few environmental restoration projects anywhere in the world operate at such scale. Despite widespread support, the project has not been without controversy. Large infrastructure projects rarely proceed without challenges, and the EAA reservoir is no exception. Construction timelines have shifted over the years as engineers encountered technical, regulatory, and logistical obstacles. Costs have also increased as project requirements evolved. Some stakeholders argue that restoration efforts should move faster, while others question whether such a complex system can fully restore historical conditions. Agricultural interests, environmental organizations, water managers, and local communities sometimes disagree on how South Florida's water should be managed. Balancing flood protection, farming, urban water supplies, and ecosystem restoration remains extraordinarily difficult. Even supporters acknowledge that no single project can fully restore the original Everglades. Instead, the reservoir forms one critical component within the much larger Comprehensive Everglades Restoration Plan, one of the most ambitious ecosystem restoration programs ever undertaken.
For more than a century, humans reshaped South Florida to control water. Today, engineers are attempting something even more ambitious. They are trying to teach water how to flow naturally once again. If successful, the Everglades Agricultural Area Reservoir could help restore ecosystems, protect drinking water supplies, reduce harmful discharges, and reshape the future of South Florida for generations. Because sometimes the greatest engineering challenge is not building something new, it is rebuilding what was lost.